Hello everybody, my name is Iman. Welcome back to my YouTube channel. Today we're going to go ahead and finish the second half of chapter 20. Now, previously we've learned how to name carboxylic acid derivatives, and we learned the basics of acyl nucleophilic substitution reactions. Now we're going to focus on the preparation and reaction of each carboxylic acid derivative. We're going to cover acid chlorides. We're going to cover anhydrides, acid anhydrides. We're going to cover esters. We're going to cover amides and nitriles. And we're going to build a profile for each one of these reactions. So let's get started. And we're going to get started with acid chlorides, acid halides in general. We're going to focus on acid chlorides here as an example, okay? Now, to prepare acid chlorides can be formed by treating carboxylic acid with thionyl chloride. That's SOCl2 here. The mechanism really has two parts. All right, the first part of the mechanism converts your oxygen group, your OH group, into a better leaving group, which is accomplished in 3 steps. That's nucleophilic attack, loss of a leaving group, and proton transfer to form this better leaving group. Now, part 2 of the mechanism is a typical nucleophilic acyl substitution, all right? And it's going to be accomplished in 2 steps, nucleophilic attack and loss of leaving group, as we have seen before, all right? And so we can have this chlorine group attack our electrophilic carbon. We form this tetrahedral intermediate. Then we reform our double bond and we lose a leaving group, which is this leaving group that we have formed in our first part, and as such we form our product, which is our acid chloride. Now, the reactions of acid chlorides are many. We can convert acid chlorides back to carboxylic acids into esters and amides and anhydrides. And so here are the reactants that we need to convert each one of these reactions. Hydrolysis of acid chlorides will take our acid chloride, treat it with water, and what we get back is our carboxylic acid. Alcoholysis of our acid chlorides will take our acid chloride, treat it with this ROH group and pyridine to form an ester. All right. Aminolysis of acid chloride will take our acid chloride, treat it with an amine, and what we form is this amide group product instead. Now, what we can also do is reduce our acid chloride, okay? And we're going to use a reducing agent that we have seen so many times before. That's lithium aluminum hydride. Now, the reduction of acid chloride to lithium aluminum, the reduction of acid chloride with lithium aluminum hydride consists of 4 really big steps. You have your nucleophilic attack, that is followed by loss of a leaving group, and then another nucleophilic attack and a final proton transfer to do that. Now, really, just make sure you know that lithium aluminum hydride is a really powerful reducing agent and will be used repeatedly for reducing carboxylic acids or aldehydes and ketones, as you have seen in previous chapters before. All right. Now, we can even treat, in addition to reducing acid chlorides, we can treat with Grignard reagents to convert acid chlorides to alcohols and introduce 2 alkyl groups. So if we have our acid chloride here, we can treat it with this magnesium bromide complex. All right, this R group can be any sort of alkyl group. It can be an methyl, an ethyl, whatever group you want it to be. What happens to our acid chloride is this carbonyl group becomes an alcohol group, and we add 2 of the alkyl groups we had attached to our magnesium bromide complex. All right, here is the mechanism for this. All right, you have the nucleophilic attack of your Grignard reagent. All right, and at the electrophilic carbon, you reform the double bond and kick the chlorine. Then you retreat it with your Grignard reagent one more time. Break the double bond here. You have this tetrahedral intermediate, but you want to reform the double bond. You won't reform the double bond here, but you'll have a proton transfer to get your final product of an alcohol group and 2 alkyl groups from your Grignard reagent. So what we have here is a nice summary. All right, you start with your acid chloride. Okay, you can convert it to an ester or an anhydride. You can convert it to amide of different forms. All right, and this is all the reagents you can do to form amides, or ones that are primary substituted or secondary. All right, you can reduce your acid chloride. Okay, you can treat with Grignard reagents to get alcohol groups and 2 alkyl groups in addition, and you can also introduce a new alkyl group in replacement of this chlorine group without changing this carbonyl with this copper lithium complex here. And we might see this again in synthesis problems, but this is a very good summary of all the things you can do with acid chloride. So draw it out yourself, practice, make sure you know the reagents you need to do every single one of these procedures. All right, fantastic. Now what we want to do is some practice problems with what we have just learned with acid chlorides. All right, predict the major product of the following reagents. Fantastic. Well, this first set of reagent we have is just simply going to reduce. All right, it's simply going to reduce our starting material. Now, what is this going to look like? Well, if it's going to reduce, then what happens is this carbonyl will be alcohol. All right, and we're going to draw it as such. Ooh, where's my pen? All right, so we're no longer going to have that chlorine group anymore. We've reduced this to an alcohol here. All right, and now what we have here are just hydrogens instead. Okay, so this is our product for A. Now for B, all right, look at this. This is our Grignard reagent, magnesium bromide. Okay, so that means our carbonyl is going to turn into an alcohol, and we're going to introduce 2 groups of this phenyl group here. Okay, so let's draw this out. Okay, this is going to turn into an alcohol, and we're going to introduce 2 of the phenyl groups here. And this is our product. All right, fantastic. Let's do one more here really quickly. Identify the reagents that can be used to achieve the following transformation. We're starting with a primary alcohol. We want to get an acid chloride. First step we have to do is we know how to convert this primary alcohol to a carboxylic acid. We need a strong oxidizing agent for this. So we're going to do sodium. We're going to use sodium chromate acid, and we're going to use sulfuric acid and water. This is going to oxidize our primary alcohol into a carboxylic acid. Now we can take our carboxylic acid. We know how to convert our carboxylic acid into a carboxylic acid derivative, specifically an acid chloride. We covered this. We need SOCl2, thionyl chloride. All right, this will do this reaction for us, and we can convert our carboxylic acid into acid chloride. Fantastic. All right, now what we want to move on to is acid anhydrides. Now, carboxylic acids can be converted into acid anhydrides with excessive heating. All right, with excessive heating, you can react carboxylic acids with each other and produce acid anhydride. This method really is only practical for acetic acid, as other acids cannot survive excessive heat. So another alternative method for preparing acid anhydrides involve treating an acid chloride with a carboxylic ion, which functions as a nucleophile. All right, so these are the 2 preparation methods we can have. If we have acetic acid, we can treat it with itself at high temperatures, acid anhydrides. We can also take acid chloride, treat it with this carboxylic ion, all right, and we can form an anhydride. Now here is a very nice diagram to summarize our acid anhydride reactions as well. So if we have acid anhydride, we can convert it into an ester just by treating it with this ROH group. We can convert it to an array of amides that are either just amides, or the nitrogen is primary or secondary. All right, it just depends on our amine nucleophile that we treat it with. We can also reduce anhydrides, all right, where we form a alcohol at this carbonyl and the rest of the group just turns into hydrogens. We can treat it with a Grignard reagent, all right, and convert, again, the carbonyl to an alcohol group and introduce two new alkyl groups. We can introduce a new alkyl group without compromising the carbonyl group using this copper lithium complex. All right, let's go ahead and do a few practice problems really quickly. All right, here's our starting material. We're going to treat it with this new group. What that means is we have our acid anhydride. We're going to treat it with this ROH group. So what happens here is we no longer have our anhydride anymore. Instead, we're going to be introducing the OR version of our OR group, okay? So here we have ROH, right? This alcohol group attached to some R group, which in this case is an aromatic ring. We're going to go ahead and attach the alcohol and the ring here to our acid anhydride. This is what happens when you treat an acid anhydride with some alcohol group that has an alkyl group attached to it. All right, let's do B now. This was A. B, we're treating it with this secondary amine. So what happens to our anhydride is instead of having the anhydride part of this is going to now be replaced with a nitrogen and the two groups that are attached to the nitrogen, to the nitrogen. All right, fantastic. All right, now we want to move on to ester. Ester preparation. When treated with a strong base followed by an alkyl halide, carboxylic acids are converted into esters. All right, so when we treat a carboxylic acid with a strong base and an alkyl halide, carboxylic acids are converted into esters. Carboxylic acids are converted into esters when treated with an acid. All right, with an acid, carboxylic acids are converted into esters when treated with an alcohol in the presence of an acid catalyst. All right, now this process specifically, all right, treating with an alcohol and an acid catalyst to get ester is called Fischer esterification. All right. Here you can see the method of this process specifically. All right, if you're starting off with a carboxylic acid, you can treat it with an alcohol in the presence of acid catalyst. You first have this proton transfer to the carbonyl group, the oxygen of the carbonyl group. Then you can have a nucleophilic attack of your alcohol. Then with a proton transfer, with a few proton transfers and a loss of a leaving group, all right, you can reform this double bond, but your oxygen still has this hydrogen, but now you've attached this ester group to it, all right, and then you just do one more proton transfer to get your ester carboxylic acid derivative. Okay, fantastic. Now, you can treat an acid chloride. You can treat an acid chloride with an alcohol group and pyridine to also get an ester. So we're treating an acid chloride, which is already a carboxylic acid derivative, right, with an alcohol group and pyridine this time. And what we can do is we can change this chlorine group to an ester group where we introduce an oxygen and whatever R group was part of our alcohol. All right, now there are other reactions of esters that we can have. Reactions of esters can consist of saponification. All right, what this is esters can be converted back into carboxylic acids with what? By the treatment of sodium hydroxide, all right, followed by an acid. All right, so esters can be converted into carboxylic acids by treatment of sodium hydroxide followed by an ester, and this process is called saponification. All right, here is the mechanism of saponification. Your alcohol groups attacks your electrophilic carbon, breaks the double bond. Now you have this sort of tetrahedral intermediate. All right, you reform the double bond. All right, and you get a loss of a leaving group. All right, your loss of a leaving group is this OR group, okay? Now you've reformed your double bond, you've lost your OR group, you have this alcohol group now. What you can do is also, here you've had your carboxylic acid, you can further do a proton transfer to get an alkoxide ion, which is generating this carboxylate ion. All right, now, esters can also be hydrolyzed under acidic conditions. I cannot pronounce that word. So acid catalyzed hydration is going to be the reverse of our Fischer esterification process, okay? So you can go back and forth. Here's your ester. You can go back to a carboxylic acid. You just treat it with a strong acid. This is the reverse process of our Fischer esterification, where we started with a carboxylic acid, we converted it into an ester. So our mechanism will also be the reverse of that. All right, now, esters can react slowly with amides to yield amides. All right, so if you treat your ester carboxylic acid derivative with amine, you can form amides. All right, so that is a very important reaction of this. You can also reduce your ester. And what are we going to reduce it with? Our good old lithium aluminum hydride. What happens here is our carbonyl becomes an alcohol group and we reduce it. So now we just have hydrogens in that position instead of this group. All right, here's again the process of reduction of an ester with lithium aluminum hydride. It is a very similar mechanism as we have seen with the reduction of all the other carboxylic acid derivatives as well. Now, something fun. You can treat your ester with something called DIBA and water to reduce only partially. All right, so this ester group can be partially reduced to just one hydrogen, but you preserve the carbonyl here. All right, that's important. This can potentially be used as an important strategy in synthesis problems. Now, to top it all off, you can treat your ester, all right, with Grignard reagents. All right, you can treat it with Grignard reagents. Okay. Oh, I didn't write this here, so you can treat it with RMGBr and water. And what you can do is now this carbonyl, all right, gets transformed into an alcohol group at the end, and you get to add your two alkyl groups, whatever they might be. Might be methyls, might be ethyls, might be phenols, whatever it is. All right, so let's go ahead and actually do a few practice problems that will summarize all the preparation and reaction methods that we have talked about in regards to esters. All right, so let's look at this first problem here. Okay, here's our ester. We're going to treat it with lithium aluminum hydride. All right, that means what we're going to do is we're going to reduce this. All right, that means that this group turns into an alcohol group, and instead now in its place, we have hydrogens. Okay, fantastic. So that's how you do your reduction process. Now, if we look at B, all right, we're treating our ester, oh, look at that, with Grignard reagents. So that means our carbonyl is going to get converted into an alcohol group, and we're going to introduce two groups of ethyls. All right, we're going to introduce two groups of ethyls. Here's an ethyl, and here's another ethyl. And this is what our product looks like. All right, fantastic. Now we can get into amides. With amides, amides can be prepared from any one of our carboxylic acid derivatives. You can just treat it with amines. You can treat with any of our carboxylic acid derivative, acid chlorides, acid esters, acid anhydrides. Treat any one of these with amines, and you get an amide. All right, that is fantastic. Now, among these methods, amides are most efficiently prepared from acid chlorides. Now, acid halides are the most reactive of the carboxylic acid derivatives, so they're going to yield, so the yields are the best when acid chlorides are used as starting materials, and that's for any one of those reactions, starting with acid chloride and transforming to acid anhydride, to esters, to amides now, very efficient and will yield the best. All right, now reactions of amides. Now, reactions of amides consist of a few things. Amides can be hydrolyzed to give carboxylic acids in the presence of aqueous acid. So we take our amide, all right, we introduce aqueous acid, we can convert it into carboxylic acid. The thing that you need to know about this is that it's a slow process, and the way that you can crank it up is with a little bit of heat. All right, but be careful with your heat. All right, here's the mechanism for acid catalyzed hydrolysis. All right, you're starting off with your amide. Okay, treating it with aqueous acid, that is going to protonate. This is going to protonate your amide. All right, and then what happens is your water can come attack your electrophilic carbon. Okay, add itself there. All right, and then deprotonate the water here via a proton transfer. Now, through another proton transfer, okay, the amino group is converted to a better leaving group. Fantastic. Now we can do loss of a leaving group. Our amide can leave, and in the process of that, we're actually reforming our we're reforming our double bond, and then our ammonia group is leaving. Okay, so now we've reformed our carbonyl group. Through one more proton transfer, we have reached our carboxylic acid. All right, so this is the mechanism for acid catalyzed hydrolysis. Protonation of the carbonyl group. All right, then water functions as a nucleophile and attacks the carbonyl group. Then the positive charge is removed from the water that we have added. Then the amino group is converted to a better leaving group through a proton transfer. Then the carbonyl group is reformed, and then because of that, our ammonia is expelled. The positive charge on our carbonyl oxygen is removed via deprotonation, and guess what? We have gotten our carboxylic acid. Now you can do this process with base catalyzed hydrolysis as well. If you have your amide, you can treat it with sodium hydroxide and heat, and then this hydronium, and then what you can do is convert your amide into carboxylic acid, and the mechanism for this follows nucleophilic attack. Your hydroxide functions as a nucleophile, attacks the carbonyl. All right, then the carbonyl group is reformed, and as a consequence, expelling the amide ion as a leaving group. And then through one more proton transfer, then you've gotten your carboxylic acid. Actually, if you do one more proton transfer, you can actually get a carboxylic ion if you wanted. Okay, now same, amides also can be reduced. Same reagent, lithium aluminum hydroxide. Okay, we're going to go ahead. We're going to do a few practice problems now. Okay, A, we have our amide. Treating it with excess lithium aluminum hydride, we're going to reduce this down. Okay, and if we reduce it, we're going to form this NH2 group here. All right, and this carbonyl has been converted to hydrogens. All right, and this is our product here. All right, now, what if we treat this acid chloride with excess amide? All right, if we treat it with excess amide, then what we're forming is our acid chloride gets converted to an amide. Fantastic. All right, now we're going to cover one last group. Our last group here is nitriles. Okay, we can prepare nitriles, and this is how we're going to do it. Okay, nitriles can be prepared by treating an alkyl halide with cyanide ion. All right, if we treat this alkyl halide with cyanide, with cyanide ion, we're gonna get an SN2 reaction here, where our bromide is replaced with this cyano group. All right, fantastic. This is some throwback to chapter 7, our substitution reaction. All right, now, nitriles can also be prepared via the dehydration of an amide. So if you start off with an amide, all right, and treat it with your thionyl chloride, all right, SOCl2, okay, you can get this cyanide group right here. Now, in aqueous conditions, nitriles can be hydrolyzed to afford amides. All right. So if you have your nitrile right here, okay, and you treat it with some strong acid and heat, you can form an amide. Now, you can take this amide, and if you're, in a good mood, you can treat it further with more acid and get back your carboxylic acid. All right, you can do this via acid hydrolysis. You can do this using basic conditions as well. Either or can take your nitrile to an amide and then can take your amide further to a carboxylic acid. All right, here is the mechanism for both acid catalyzed hydrolysis of nitriles and base catalyzed hydrolysis of nitriles. Okay, so for acid catalyzed, you're going to have a proton transfer. Protonation of the nitrile group is going to make it more electrophilic, and then your water can function as a nucleophile and attack. All right, then the positive charge on your water is removed. All right, and then the nitrogen atom is further protonated, okay, forming a resonance stabilized intermediate. Here's your resonance stabilized intermediate. Then through a proton transfer, you can get your end product. All right, now base catalyzed hydrolysis of nitriles to get this amide that we're looking for, okay, involves a nucleophilic attack where your hydroxide functions as a nucleophile and it attacks the cyano group. All right, then the negative charge on the nitrogen is removed via protonation. All right, then your hydroxide functions as a base. It removes this hydrogen from this alcohol groups, and as a consequence forms this resonance stabilized intermediate, which just needs a proton transfer for us to form our amide product. All right, now nitriles can also be treated with Grignard reagents. Fantastic. What this looks like is if you treat it with Grignard reagent, all right, at this carbon, you're going to form a carbonyl group, and you're going to introduce whatever alkyl group you have that is attached to your magnesium bromide complex. All right, so this is how Grignard reagent proceeds with nitriles. Now, you can also reduce nitriles, all right, through the use of lithium aluminum hydride. What happens here is this triple bond to nitrogen is now just a single bond to an amine group. All right, and your carbon now is reduced and has hydrogens. All right, fantastic. Let's do a couple practice problems here. All right, let's do a couple problems here. Fantastic. Now, if we take this group, all right, this is our nitrile group, and we reduce it, what kind of product are we going to get? Well, we're going to get the following product. Let's draw this out. All right, the carbon stays, but now it no longer has a triple bond to nitrogen. Now it's going to have a single bond to an amine group. And here, all right, are hydrogens, right? Because we've reduced it. Now we can also do the second problem. Ooh, it doesn't want to zoom in for me. There we go. Sorry about that. All right, here we have this aromatic ring that has this bromine group here. Now our first set of reagent is going to do a SN2 reaction here where we convert the bromine to a cyano group. All right, fantastic. Now we have our nitrile. We can further treat it with, oh, look at that. Okay, this is Grignard reagents. Now what happens with Grignard reagents when you treat it to a nitrile is this carbon here, all right, no longer has a bond to nitrogen. It no longer has a triple bond to nitrogen. It's going to have a carbonyl group here, and then whatever R group was part of your magnesium bromide complex, which is methyl. So this is our product when we treat this starting material with cyanide, all right, and then Grignard reagents. Fantastic. All right, now we've covered the preparations and the reactions of 5 groups of carboxylic acid derivatives. acid chlorides, acid anhydrides, esters, amides, and nitriles. All right, we've built a profile for each one of these. Now let's do a few synthesis problems. Identify reagents that will accomplish each one of the following transformations. All right, so if we start with this first group here, all right, we have an ester. All right, we have an ester, and we want to convert it to, oh, look at that, an acid chloride. How can we convert this to an acid chloride? We cannot straight away take an ester, and carboxylic acid derivative, this ester, and go straight to chloride. All right, why? Because acid chlorides are way more reactive than esters. So if you just try to treat this with straight up thionyl chloride, all right, thionyl chloride, what's going to happen is you're just going to keep reforming the ester, because your chloride, when you introduce it, is just going to be such a good leaving group, it will repeatedly leave. So our technique here, our strategy has to be different. We cannot just treat this ester right away with one reagent to get acid chloride. We actually have to convert it back to a carboxylic acid using strong acid. All right, convert it back to a carboxylic acid, and then from the carboxylic acid, go to the acid chloride through the treatment of our thionyl chloride. All right, so that is how we can do that. All right, let's try to do B now. All right, and I'll leave C and D for you to make an attempt. Let me see what B looks like. Okay, let's draw this out. All right, we're starting off with carboxylic acid. We are trying to form, all right, this group right here. Okay, now what we can do, one way we can do this is actually, we can take our acid chloride, our carboxylic acid that we're starting off with, and convert it to acid chloride, to a carboxylic acid derivative. All right, now that we have our acid chloride, what we can do is convert it to a amide. Easy. Excess amine will convert our acid chloride to an amide. Now that we have our amide, we can easily reduce this to get our end product. And how do we reduce this? Easy. Lithium, aluminum, hydride, and water. Fantastic. All right. Now that's all I have for you for this chapter. We have finished chapter 20. Yay. All right. Let me know if you have any questions, comments, or concerns in the comments below, or feel free to email me if you're stuck on a problem and you need help. Other than that, happy studying, good luck, and have a fantastic day.